Hello, dear students. Today we are dealing with the following issue, which reveals the use of electromagnetic radiation in medicine. Well, we will also get acquainted with another type of electromagnetic radiation. This is X-ray radiation, methods of production, basic properties, characteristics of interaction with body tissues. And we will also analyze the issues that relate to the use of X-ray radiation for diagnosis and also therapy. As for the discovery of X-ray radiation, it was discovered by X-ray. His portrait can be seen on the slide, and the years of his life are also shown here. This is a German physicist who worked at the University of Urbis in 1895 year, conducted research in which he just noticed an unusual bloom. The glow of platinum of barium cyanide concluded that this was some unknown early radiation, although scientists had also encountered X-ray radiation earlier, but they did not pay much attention to this glow. Here, the X-ray wrapped the X-ray tube in paper and then already noticed the glow of the initiating screen. I concluded that this is some kind of new glow, made a study of this study. It was originally called their cases. And then, in honor of the discoverer, the person who described X-rays in sufficient detail, X-ray radiation was named after X-ray. In 1900 and the first year, X-ray was awarded the Nobel Prize for the discovery of X-rays. Here we have shown one of the first photos that was made using X-rays. This is the hand of a friend of X-ray. He also took photographs of his wife's hands in X-rays, but these are just the first pictures that were obtained using X-rays. As for our attention to this issue, we must not forget that there is no credit ahead. And just the questions that relate to X-ray radiation are taken out for a special test. Well, here you can just see the main questions that you need to rely on when preparing for the first test. That's exactly what concerns X-rays. Application in medicine will be briefly considered. Then, at the end of the lecture, we will dwell on these issues in more detail. In other words, it is widely used, but still the limitations of the use of X-ray radiation are still associated with the radiation load, with the ionization of X-ray radiation by a substance. Therefore, we can use X-rays to a limited extent, but we use them for angiography in order to find out the condition of the vessels. We also use it for fluoroscopy. In the modern form, fluoroscopy can be represented as an X-ray of television transmission, dentistry, orthophantomography. Then here we get a picture of all the teeth at the same time. It is also possible to use X-ray radiation for the treatment of neoplasms. This is X-ray therapy, computed tomography. X-ray tomography, in another way, we can also call this type of examination. X-ray radiation is also used here. Everyone knows fluorography. It is also based on the use of X-ray radiation. Well, radiographs are quite often used. Here we get an image on a photographic film, a photographic plate, and then, based on the received image, we conclude about the condition of these organs or a limb, if it is a fracture, for example. In other words, X-ray radiation can be used quite often in medicine. But before we deal with radiation, we need to find out the properties of X-ray radiation, and also need to figure out how to get X-ray radiation, how X-ray radiation acts on the human body. We recall again that X-ray radiation is electromagnetic radiation, and if we look at the scale of electromagnetic radiation, then we will have X-ray radiation between ultraviolet radiation and between the gamma of radiation. According to its properties, X-ray radiation, of course, we will have different depending on the purity, on the wavelength. In other words, the higher the frequency, the correspondingly the properties are closer to gamma radiation. If the purity is less, the wavelength is longer, then it is more properties that relate to ultraviolet rays. Well, just like any electromagnetic radiation, our X-ray radiation will be absorbed by tissues. It is also possible to reflect X-rays. As for the nature of X-rays, it can be noted that this is an electromagnetic ionizing study, that is, at certain energy values, ionization of atoms and molecules occurs. Well, as I have already said, it occupies that this radiation occupies the spectral region between gamma and ultraviolet radiation. Well, as for the spectral region, after all, there is no clear division by frequency. By wavelength, there is an overlap of the ranges of X-ray radiation and ultraviolet radiation, X-ray radiation, and gamma radiation. In other words, we determine the X-ray radiation depending on the method of obtaining. Well, as for the wavelength, after all, here we have a wavelength that will be in the range from 10⁻⁴ to 10⁻³ angstrom. 1 angstrom is 10 minus the 10th degree of a meter. Well, with sufficiently small values of the wavelength, the size of the atom, we also use this characteristic, that is, the angstrom, or we can also use such a unit as a nanometer. That is, in this case, we are talking about the fact that the wavelength will be from 10⁻⁵ to 100 nanometers. Well, you can see the scale again. We have already looked at it when we analyzed electromagnetic waves, but here we see that X-ray radiation overlaps with ultraviolet and gamma radiation. Therefore, the properties of X-ray radiation, of course, will depend on the purity, on the wavelength. We said that X-ray radiation is an electromagnetic wave. Well, let's remember what an electromagnetic field is. That is, it is a set of alternating electric and magnetic fields that are interconnected and mutually generate each other. Well, if we talk about an electromagnetic wave, then this is the propagation of an electromagnetic oscillation in space. That is, in the case when we talk about the presence of an electromagnetic wave, we say that in this case, we have an electromagnetic oscillation propagating in space. Properties of X-rays. It is precisely the properties that determine the use of X-rays. The first property is invisible to the eye. In other words, X-ray radiation also refers to electromagnetic waves as well as visible radiation, which we can fix with the help of the organ of vision and can navigate in space. But since the wavelength here is quite small, our visual organ is not able to perceive this radiation. The next thing is that our X-rays cause luminescence of a number of substances. Just this property allowed the X-ray to open these rays. Well, in medicine, we use this property to create special screens for visual observation of X-rays. That is, some substances are able to luminify by the actions of X-ray radiation. The following: X-rays ionize air as well as other gases. This property is used to quantify X-ray radiation for dosimetry. In other words, we need to know what dose of X-ray radiation the patient will receive, and it is also necessary to assess the possible impact. Well, this is when the device is created accordingly. It is necessary to take into account the radiation load that the patient will receive. The next thing is that it has photochemical effects, that is, it illuminates the photoemulsion. Also, This property is used to register X-rays that have passed through the tissues of the body, and then we can already draw a conclusion about the state of this organ on the photographic film, depending on how the illumination of this photographic film occurred. The following X-rays have a penetrating ability, that is, the human body penetrates through. We also use this property of diagnostics, that is, we have X-rays passing through the tissues. They will come out of some certain intensity, and then we already evaluate the picture. In addition, these are also properties that are used in diagnostics. X-rays are absorbed by the substance differently depending on the elemental composition of the substance, depending on its thickness. In other words, calcium absorbs, for example, X-rays more strongly than the same oxygen, or one might say water. In addition, X-rays are biologically active because they cause ionization of substances, cause DNA damage, and this can lead to negative consequences with a high dose of X-ray radiation. The following property, well, it most likely says that after all, X-ray radiation differs from low-frequency electromagnetic radiation of the radio band, that the thermal effect is quite small, that is, just like X-ray radiation, as well as low-frequency radiation of the radio band is an electromagnetic wave, but there is practically no typical effect here. And the ninth property that we must take into account when creating protection against X-rays is that X-rays will be scattered by passing through the substance. In other words, we need to take into account that protection needs to be carried out not only in the forward direction, but also in all directions, to take into account the fact that X-rays will be scattered in our country. This concerns the properties of X-rays. Well, as for the sources of X-ray radiation, many celestial objects of the Sun's star are a source of X-ray radiation, but the Earth has an atmosphere. Therefore, as we have shown here, shortwave X-ray radiation will be absorbed by the atmospheres. Therefore, natural sources, celestial sources we do not have, do not pose a danger to the body. In addition, we also have radioactive decay, and radioactive decay can also be accompanied by X-rays. And besides, there are also artificial sources of X-ray radiation. These are the same X-ray tubes that are used in medicine, are also used in industry, are also used at the airport in order to find out the presence of dangerous items in luggage, for example. So, well, the next question is how to get X-rays. In other words, we need to figure out how to get X-rays, and here it is possible to distinguish two types of X-ray radiation. This is breaking and characteristic. As for breaking, it can be said that X-rays are always received when charged particles are decelerated on a solid target. And in this case, the energy of electrons or other charged particles is converted into the energy of electromagnetic radiation. Well, that is, X-ray radiation. In addition, the appearance of characteristic X-ray radiation is also possible. It is obtained during quantum transitions on layers of an atom close to the nucleus with a high ordinal number. Just as the breaking characteristic X-ray radiation can be obtained using an X-ray tube, if you increase the voltage of the X-ray tube, increase the electron energy, then there will be a knocking out of electrons from the inner layers and electrons from the overlying layers move to the vacant place, while energy is released in the form of characteristic X-ray radiation. But the main source of X-ray radiation is an X-ray tube. Let's see what she is like. Well, first of all, they say it's an electric vacuum cylinder. Well, in this case, we have a pressure in the X-ray tube of about 10⁻⁷ 10⁻⁶ millimeters of mercury. That is, a sufficiently low pressure in the X-ray tube should be maintained. In addition, this tube contains a cathode. That is, here we have shown and designated by the letter K, and also the anode is marked with the letter A. The cathode is negatively charged, the anode is positively charged. In addition, the cathode is our electron source. Electrons. Well, in order for our electrons not to descend, it is necessary to heat the cathode, that is, here we have a filament connected. When the cathode is heated, electrons descend. But in order for X-ray radiation to occur, we need a sufficiently high voltage to exist between the cathode and the anode. Then here the voltage fits on the order of 100 kilovolts. Well, depending on some kind of X-ray tube, where it is used, well, somewhere from 20 kilovolts minimum to 150 kilovolts. In other words, our electrons must accelerate, and as they accelerate, they acquire kinetic energy. Then they interact with the working substance of the anode, and the working part of the anode must be made of a refractory metal, and most often metals with a high serial number are still used. We'll also figure out later why with a high serial number. Well, here we have shown that tungsten, platinum, and gold can be used. The main part of the anode is made of media, of metal with good heat-conducting properties. In other words, this is what concerns the structure of the X-ray tube. Well, you can write down that this is an electric vacuum cylinder, which contains two electrodes, a skating rink and it, and as for the requirements for the anode, I have already said that it is good. It is made of a well heat-conducting metal. The working part is made of refractory metal. In addition, we have a beveled surface of the anode at an angle of 45 degrees so that the X-rays come out of the X-ray tube. And besides, the working part of the anode must be mirrored to reflect X-rays. Well, you can also add that we can have a cooling system for the anode. This is an air cooling system, a water cooling system, and also an oil cooling system. Here, we have shown one of the first X-ray tubes. This is the Crookes tube. Well, the difference from the X-ray tube that we have just examined is that there was a cold cathode, and the electrons that participated in the creation of X-ray radiation were formed due to the ionization of the remaining air inside this tube. Modern X-ray tubes have a heated roller, but these are the first X-ray tubes that were originally used, and X-rays were also used. Modern X-ray tubes are already shown here, that is, we have an anode here and also a cathode with a filament. Well, another one in the X-ray tube is also shown here. As for the mechanism of obtaining X-rays, that is, in this case, we have, as we found out, a thermionic mission takes place, the cathode is heated, the electrons descend the cathode. A sufficiently large potential difference is applied between the cathode and the anode. As a result, the electrons are accelerated while acquiring kinetic energy. Initially, they acquire potential energy, then it turns into kinetic energy. The electrons in their motion collide with the working substance of the anode. And when a collision occurs, naturally, our electrons decrease their speed decreases. And we know that since we have electrons moving, in this case in principle, we are dealing with a directed flow of charged particles. That is, with an electric current, and in this case, it will be a decreasing electric current. Decreasing electric current. Alternating electric current is a source of alternating magnetic field, according to Maxim's theory. We remember, in general, any current is a source of a magnetic field, but since we have variables here, an electric field, it leads to the appearance of an alternating magnetic field, and according to Maxwell's theory, an alternating magnetic field leads to the appearance of an alternating electric field. That is, in this case, we will have a set of alternating electric and magnetic fields that will be interconnected and mutually generate each other. In other words, in this case, we come to the appearance of an electromagnetic wave, and this electromagnetic wave was called X-ray radiation. We also have a node cooling system shown here, that is, a water cooling system. This is due to the fact that the anode will heat up well enough, and in order for the anode to exist for a very long time, it is necessary to cool it so that it does not collapse ahead of time. And so it is possible to write down in more detail what happens in the X-ray tube, which leads to the appearance of an electromagnetic study of X-ray radiation. That is, initially we have a thermionic mission emitting electrons from the cathode. And then we have acceleration of electrons initially, then their deceleration when the working part of the anode is inserted, and then, since we have the movement of charged particles, it will be an electric current. This electric current is decreasing. There is a magnetic field. Well, the decreasing magnetic field leads to the appearance of an alternating electric field, and the combination of these fields will be just an electromagnetic wave for us. Due to the fact that we have a deceleration of electrons, an alternating magnetic field appears and then an electromagnetic wave already occurs. As an example, you can see in general what situations are possible depending on how the electron moves. That is, if we have an electron at rest, then its velocity will be constant. It is clear, and in this case, an electrostatic field arises. If we have an electron moving at a constant speed, naturally, we get a constant current and a constant magnetic field. That is, in this case, we will no longer have an electromagnetic wave, but in the event that we have an electron velocity that is not constant, that is, the electron interacts with the anode atoms. When introduced into the anode, that is, breaking also occurs due to the fact that the electrons that are in the orbits of the atom will act on the electron with a repulsive force. There will also be a force of attraction to the core. Well, in this case, we have a deceleration of electrons, an alternating current occurs. Any current is an alternating current source. Any current is a magnetic field source. In this case, it will be an alternating magnetic field, and an alternating magnetic field, according to Max's theory, leads to the appearance of an alternating electric field. As a result, we get an electromagnetic wave. That is, in this way, we come to the appearance of an electromagnetic wave due to the fact that the electron is decelerated. When generating X-rays, we also have the law of conservation of energy. Initially, the electron acquires potential energy. Our potential energy is equal to the product of the electron charge by the voltage between the anode and the cathode. Then, with acceleration, this potential energy turns into the kinetic energy of the electron, and here we have kinetic energy as the product of the mass of electrons squared by the electron velocity, well, divided by 2. During deceleration, the kinetic energy of the electron in interaction with the anode atoms is converted into the energy of the X-ray quantum, and the energy of the X-ray quantum is defined as Planck's constant multiplied by the frequency of the X-ray quantum. Based on this formula, we can conclude that the greater the voltage between the anode and the cathode, the greater the frequency of X-ray radiation, but the wavelength, respectively, will be less, because the purity and wavelength are inversely dependent on us. The next question we have concerns the continuous spectrum of X-ray radiation, and here on this slide we have shown the dependence of the intensity of X-ray radiation. The same kind of dependence will have a dependence of the X-ray radiation flux of the wavelength. In other words, we see that our spectrum will be continuous, and it starts from the minimum of some wavelength value, and then there are already many lengths in this spectrum. In other words, our X-ray spectrum is continuously distributed over all new ones, starting from the shortwave boundary of the lambda minimum spectrum. Well, depending on the voltage, we see that the shortwave boundary of the spectrum will have different values. But the fact is that we have considered the law of conservation of energy. According to the law of conservation of energy, at a certain voltage value, the frequency of X-ray radiation must be strictly determined, and the wavelength must be strictly determined. In this case, then, we should not observe a continuous spectrum. In other words, here we have a contradiction. Why, along with the fact that the law of conservation of energy is fulfilled, we have a continuous spectrum. The fact is that we have a random breaking of electrons, then the degree of breaking will be different. In addition, we have already said that the X-ray tube will heat up. Therefore, part of our energy will be converted into thermal energy. And in the case when part of our energy is converted into thermal energy, those photons that do not correspond to the shortwave boundary of the spectrum, they will be determined by us just. That is, in the case when we have heat losses, we will have X-ray radiation, a wavelength that is greater than the shortwave boundaries of alcohol, but the purity accordingly will be less. This is what determines the shortwave boundary of the spectrum. That is, in this case, we will have a continuous spectrum, and the heat loss will be determined by the fact that our radiation spectrum will be continuous. The shortwave boundary of alcohol will be observed only when we have all the energy of the electron converted into the energy of the X-ray quantum. The next question is the X-ray flux. The X-ray flux is determined by the following formula. This is the proportionality coefficient of 10 minus the 9th volt minus the 1st degree, multiplied by the current strength of the X-ray tube, multiplied by the voltage between the anode and the cathode squared, and multiplied by the ordinal number of the working substance of the anode. Well, let's look at the graph, how our flow changes depending on which characteristic of the X-ray tube changes. That is, if we change the serial number of the working substance of the anode, we see that the flow will increase. Why is there an increase in flow? Because the interaction will be stronger. In other words, the more we have an ordinal number, the more electrons in the orbits of a given one, the stronger it will interact. That is, at the same voltage value, with an increase in the ordinal number, we will observe an increase in the flux for atoms with a large order. If we increase the voltage, then the flow will also increase. Well, the shortwave boundary of the spectrum also changes. That is, in this case, we will have a shift of the shortwave boundary of the spectrum towards smaller wavelengths. With an increase in voltage, well, the flow also increases with increasing voltage. What is the reason for this? This is due to the fact that with an increase in flow, with an increase in voltage, we will have an attraction of electron energy, and electrons in greater numbers will reach the anode. And also the energy will be greater, the interaction will be stronger, and besides, we also have an X-ray flux that depends on the current strength, well, or from the cathode temperature. The greater the current strength, the greater the temperature of the filament, the cathode, and accordingly, the greater number of electrons will be emitted from the cathode. As a result, a greater number of photons of X-ray radiation will be received. In other words, the current strength increases, the temperature increases, the flow will also increase, but the shortwave boundary of the spectrum will be constant because it depends only on the voltage. In other words, the graph will look like this, as for the case when we increase the serial number of the working substance of the announcement. Well, of course, there will also be a dependence on the current strength. Well, the shape of the graph will be similar. This concerns the dependence of the X-ray flux on the characteristics of the X-ray tube. The next question is the shortwave boundary of the spectrum. The shortwave boundary of the spectrum can be found from the law of conservation of energy. That is, if you look at the law of conservation of energy, we have potential energy there and also the energy of a photon. We can have the photon energy painted as much as multiplied by the frequency of the X-ray quantum, or we can determine the frequency in terms of the wavelength, that is, c divided by law. We have Planck's constant, a value that does not change. The speed of light also does not change, and the charge of the electron does not change. We can write down this formula for the shortened boundary of the spectrum. The minimum lambda is equal to 12 as much as 3/10 divided by the voltage between the anode and the cathode. In this case, we will receive the shortwave boundary of the spectrum in angstroms, that is, 10 minus the 10th power of a meter. In this case, we substitute the voltage in kilovolts. Well, based on this, we can conclude that the shortwave boundary of the spectrum depends only on the voltage between the anode and the cathode. The purity of the X-ray radiation, the wavelength of the X-ray radiation, will be determined only by the voltage. The next question is the characteristic X-ray radiation. In other words, we have sorted out what concerns breaking X-rays, and the characteristic X-ray radiation will be observed if we have an even greater electron energy of the X-ray tube. But it is just possible to achieve the attraction of voltage, for example, between the anode and the cathode. Then the energy of the X-ray, the energy of the photons of the X-ray radiation will be greater, and the energy of the electrons will also increase. That is, the electrons acquire more energy. With more energy, they are introduced into the working substance of the anode, and at the same time, electrons are knocked out of the inner layers. Electrons from the overlying energy levels move to the vacant places. We observe separate spectral lines. Since we have the energy that is released, it will be emitted in the form of X-ray quanta of characteristic radiation. We have shown here the study of the characteristic X-ray spectrum. It has a linear spectrum. That is, in this case, we will have a linear spectrum against the background of breaking X-rays. You can also see as an example the characteristic spectrum for the anode, the working part of which is represented by rhodium. Well, we see that a separate spectral line will be present against the background of a solid spectrum, which corresponds to the breaking X-ray radiation. Here we have an X-ray tube running at a voltage equal to 60 kilovolts. Well, you can also look at the mechanism of occurrence of X-rays. That is, we have an electron that moves at a very high speed. It is embedded with cotton wool of the working substance of the node, while an electron is knocked out from the inner layer and an electron from the energy level above passes to the vacant place. This releases energy in the form of a photon of X-ray radiation. In other words, this is the mechanism of the occurrence of X-ray radiation. Well, the characteristic radiation of the spectral line of the characteristic radiation will consist of a series of kilometers, h and so on. Well, depending on which orbitals quantum transitions occur between. The same thing can be seen here on the slide. In other words, we see that quantum transitions occur, and quantum transitions correspond to certain orbitals. Here, we have shown spectral lines for various substances, depending on the material, which atom in this case we use as the anode material. We see that the spectral lines will be different. For each atom, we will observe certain spectral lines. This is due to the fact that we still have the energy of different orbitals will be different. Therefore, certain spectral lines will be present for each atom, so this study is called characteristic. In other words, it characterizes exactly the atom that is the source of this radiation, and regardless of which compound a given atom is in, the characteristic spectrum of it will always be certain, unchanged, that is, the same hydrogen is it in an atomic state, a molecular state, or is in combination with water. Its characteristic spectrum will always be the same. Now we analyze the next question. This is the interaction of X-ray radiation with the atoms of matter, and the interaction is also based on the use of X-ray radiation, or rather the limitations of its use. The first type of interaction is the coherent scattering of X-rays. In this case, we have X-ray radiation with energy less than the ionization energy of a given atom. And when a photon of X-ray radiation interacts with a given atom, we only have a deviation of the X-ray radiation from the original direction. The energy, purity, and wavelength of the scattered X-ray radiation will be the same as the incident one. In other words, there is only a deviation from the original direction. Ionization of the substance does not occur, but in this case, we will not have X-ray radiation either. But it is necessary to take into account this type of scattering when creating protection from X-rays. Well, in this case, we see that the past flow will be observed and the scattered flow will also be observed. The second type of X-ray radiation is incoherent scattering, or the Compton effect. In this case, we already have X-ray radiation with a sufficiently high energy, much more than the ionization energy. Therefore, when interacting with an atom, an electron is knocked out, that is, part of the energy goes to knock out the electron. Well, the rest goes to create a secondary photon of X-ray radiation. In other words, it will be a scattered secondary photon, which can also have a sufficiently high energy and can also lead to ionization of matter in the future. In addition, we also have ionization of matter can occur under the influence of electron recoil, the electron that is knocked out of the atom. Well, in general, we can say that as for the interaction of X-ray radiation with matter, here are the phenomena that we are considering. They are primary. In fact, the interaction of X-ray radiation with matter is repeated, and it is precisely on those phenomena that we are considering now that it does not stop. That is, there is further ionization by the same electrons that are knocked out in the case of the Canton effect, and also the photoelectric effect, which we will also consider now. Here you can see the definition of this phenomenon, and that's what concerns the photo effect. In other words, in the case of a photoelectric effect, we will have less X-ray energy than in the case of the Compton effect. That is, it will be greater than or equal to the ionization energy. That is, in this case, we only have the knocking out of an electron, but this electron clogs up all the energy of X-ray radiation and can also cause further ionization of the substance. Therefore, X-ray radiation has a sufficiently high ionizing effect. If we have an X-ray photon with insufficient energy to knock out an electron, then it is possible to excite an atom of matter. Photochemical reactions are possible. In other words, this is also the case in the case of exposure to X-rays. Well, just passing through the tissues of the body, passing through the substance, we have the conversion of X-ray energy into other types of energy. And the flow that will come out of the body tissue, or from any substance, will be determined by the Blogger's law. The Blogger's law here says that the radiation flux of the released substance, and this law applies not only to X-ray radiation, but also to other types of electromagnetic radiation. So, the flow that came out of the substance will be determined by the falling flow. F0 will also be determined by the linear attenuation coefficient of the X-ray radiation and the thickness of the absorbing layer X. The linear attenuation coefficient in this case is determined as follows. K is the proportionality coefficient. It is the density of the substance that absorbs X-ray radiation. Z is the ordinal number of the substance that again absorbs X-ray radiation. And the lambda is the wavelength of the X-ray radiation that falls on a given substance. Well, here you can just look at the designations that are used in this form. In other words, the more we have an ordinal number of substances that absorb X-rays, the more it will absorb X-rays. That is, elements with a higher ordinal number absorb X-rays more strongly. The longer the wavelength, the more X-ray radiation will be absorbed again, and just soft X-ray radiation is absorbed more strongly. So it is used for therapeutic education. But hard radiation, which will linger less in the tissues of the body, it has a shorter wavelength, it is absorbed to a lesser extent, so it is used for diagnostics. And as for the division into hard-soft rays, then if the photon energy is more than 5 to 10 kiloelectrons volts, well, either the wavelength is less than 0, as much as 0.2, as much as 1/10 of a nanometer, then such radiation will be considered hard for us. If the photon energy is correspondingly less than 50 kiloelectronic volts, then this radiation will already be considered soft. In other words, this is what concerns the division into hard-soft radiation. In other words, the greater the purity, the more rigid the X-ray radiation will be. The next question is the physical basis of X-ray diagnostics. Well, at the beginning of the lecture, we discussed with you the issues that relate to the properties of X-ray study. It can be said that some properties are the basis of X-ray diagnostics. As for the fact that X-rays penetrate through the tissues of the body, the fact that we absorb X-rays, depending on the composition of the body tissue, depending on the thickness. This also applies to the Blogger's law, which we have just reviewed. In addition, we also need to register X-ray radiation that has passed through the tissues of the body, and for this, we use such properties as the illumination of the emulsion, the photochemical effect of X-ray radiation. In addition, we also use the properties of X-rays to cause luminescence of a number of substances. Well, at present, of course, we also use modern methods of registration. These are digital registration methods, digital sensors that also allow us to register X-rays. And as for the ability of body tissues to absorb X-rays in different ways, we have provided comparative ones here. The values of the absorption coefficient depending on the sequence number. That is, if we compare the degree of absorption of iron and lithium, then we see that lithium will absorb X-rays 650 times weaker, unlike iron. Well, that is, in this case, we only compare the ordinal numbers, the numbers of these substances. Well, we naturally take the third degree, because our linear absorption coefficient takes into account the third degree of the ordinal number. You can also see what is the difference between the absorption coefficient for bone tissue and soft tissue. But since our soft tissue contains a fairly large amount of water, in this case, we take the formula of water for comparison and the formula of bone tissue as well. Given the sequence number, given the number of atoms in the formula, we get that bone tissue absorbs X-rays 68 times more strongly than soft tissue. Here you can see the scheme of X-ray image formation, and we see that after the X-ray radiation passes through the tissues of the body, where we had bone tissue, the radiation intensity will be less. Well, where the lungs are, the intensity is greater. But if there is some kind of inclusion, then, accordingly, the intensity will also have less significance. That is, the flow is initially supplied to us of the same intensity, passing through the tissues of the body. The intensity of the X-ray radiation flow will change, and accordingly, the detector, either the screen or the film, will record the already changed X-ray intensity. And then, the doctor already reviews the information received, makes a diagnosis. Types of X-ray diagnostics. Initially, we have shown an X-ray. That is, here we get images on a glowing screen. Now, this type of examination in its original form is still used less often, because it is necessary that the doctor and the patient are in the same room. That is, here the radiation load on the doctor will also be observed. The advantage of this method is that we can still look at the work of the organ, And in addition, it is possible to consider from different sides, that is, the rotation of the object. Well, minus it's still quite a large radiation load. Here we have shown the device that is used in the case of fluoroscopy. Well, fluoroscopy is now replacing X-ray television transmission when the doctor is already at the computer screen, and the image is received on the computer screen. That is, in this case, we have X-ray radiation converted, well, initially amplified, and then converted using an electron-optical converter, and then fed to a computer monitor. That is, here we have the same thing shown. It is possible to save the received image here already, to consider it in detail later. In other words, these are the advantages of this method of examination. And if the electronic method of image registration is still used, then we will no longer have an electronic, digital method of registration. Then the radiation load in this case will be less. The next type of examination is radiography, which is often used. In other words, in this case we get an image on a photographic film, on a photographic plate. It is characterized by a low radiation load and sufficiently high clarity. But the disadvantages, of course, we can't look at the dynamics. We can't look at it from some other angle. If, for example, the patient has already left, we need to take a second picture. Then here we still have several chias superimposed, for example, so we do not always get complete information during this examination. Here we also have X-rays shown. And here we have a remote-controlled X-ray machine, that is, the doctor is behind the glass and watches the procedure. The next question we have can be singled out separately. It will be interesting for students of the Faculty of Dentistry. This is an orthopotenogram. In this case, it receives an X-ray image of the upper-lower jaw immediately, and at the same time, the X-ray tube and also the detector, which is located on the other side, rotate, while a digital image is formed. That is, here the radiation load will again be lower than in the case of the film method of examination. Well, here it will be 10-40 microsieverts. The next type of examination is X-ray tomography or computed tomography. The same thing. In this case, of course, the radiation load will be higher, but we get an image in three-dimensional space due to the fact that, first of all, the image is obtained from different sides. That is, here as shown, we have a rotation of both the X-ray tube and also a sensor that records the flows of X-ray radiation that has passed through the tissues of the body. Then, after we have registered the streams, these streams are processed by a computer program, and the computer already creates an image in various planes, and in this case, we can get a layered image. Here we show scientists who just invented computed tomography, and in 1979 year, they were awarded the Nobel Prize. Well, you can also look at spiral computed tomography. That is, here we have a rotation of the X-ray tube, and the sensor in a circle, but the person moves on the table, so the training takes place in a spiral. And you can see examples of learned tomography, computed tomography. Well, as in the case of X-ray, also in the case of computed tomography, we can use a contrast agent. That is, if our body tissues absorb X-ray examination to the same extent, then we use a contrast agent. Barium sulfate can be used, and a substance containing iodine can also be used. Here you can see a computer tomography of the brain layered, that is, from the base of the skull to the top of the head can be viewed. In other words, the computer gives us a layered image after processing the information received from the CORT scanner. And here we have CORT angiography, that is, an iodine-containing substance is injected into the tissues of the body and will already be observed. The image of the vessels in a contrasting way, and we can already assess the condition of the vessels. We also use X-ray examination for therapeutic education because X-ray radiation in our country is characterized by biologically active action and X-ray radiation. It will cause DNA damage, cell damage. There is also radiolysis of water. That is, it will lead to the fact that just cancer cells that are poorly differentiated, and rapidly multiplying, they will absorb X-rays to a greater extent, well, or other ionizing radiation. Therefore, X-ray radiation is used for the therapy of neoplasms. Well, we know that our absorption of X-rays occurs depending on the wavelength. In other words, it will be absorbed to a greater extent by long-wave radiation. So we use a soft study for the therapy of neoplasms. The absorption is greater and the impact will be stronger. Protection from X-rays. Our protection will also be determined by the law of the blogger. In other words, we know that the X-ray flux will decrease with an increase in the linear exaggeration of the linear absorption coefficient, and with an increase in the thickness of the absorbing layer as well. In other words, the greater the thickness of the absorbing layer, the more X-ray radiation will be absorbed by this substance. This is the first thing we can take into account. The second is the fact that metals with a higher ordinal number will again absorb radiation to a greater extent. In other words, we can increase the linear absorption coefficient by increasing the ordinal number of the substance that absorbs X-rays. Well, here we have shown the use of lead in the case of protection from X-ray radiation. That is, we use a lead apron here. That is, lead has a fairly high ordinal number. You can see this element number 82 in our periodic table. Well, of course we don't end up with lead in the periodic table, but the fact is that all the other elements are radioactive, and we can no longer use them to create protection from X-rays. And lead is the last stable isotope of the periodic table, so we use it for protection. Moreover, we can use it for protection both in its pure form. We can also use lead salts to create lead aprons. We can also use lead salts as an addition glass in the X-ray room so that our doctor can observe the patient. In other words, such protection is possible in this case. Well, here we have shown what is the possible use of what thickness of lead, depending on what energy of X-ray radiation is used. And the last question is the X-ray structural analysis of biological objects. We can evaluate the structure of substances, depending on how the X-rays pass through these substances, through their crystal lattice. That is, with the help of X-ray structural analysis, we estimate the size of atoms, we can evaluate the type of chemical bonds. It is also possible to dilute the evaluation of salts, metals, and also semiconductors. We make an assessment using X-ray radiation. And we can also study biological substances with the help of X-ray radiation of their structure. That is, proteins, nucleic acids. We also study with the help of X-ray radiation, with the help of X-ray diffraction on various structures. Diffraction is possible due to the fact that our X-ray radiation has a rather small wavelength, that is, about 10⁻⁵ I will get a meter. And if we are talking about crystal structures, then here we have dimensions corresponding to 1 angstrom, well, or 0 as much as 1/10 of a nanometer. Therefore, in this case, X-rays will experience diffraction, that is, they will go around these obstacles. Depending on how the diffraction occurs, we will observe a maximum and a minimum of diffraction, and in this case, we will observe a diffraction pattern. It is shown here that we have an X-ray beam passing through the crystal, and, depending on the structure of the crystal, a certain picture will be observed on the photographic film, for example, where the maximum of the region study will be observed. Depending on what kind of picture will be observed here, for example, here we have shown 4 tables salt. It can be concluded about the structure of this crystal, this substance, and this particular study is often used in our country to find out the structure. Well, here we have shown an X-ray structural analysis of DNA fibers. This is what concerns the use of X-ray radiation in medicine, in essence X-ray radiation. In other words, we have found out what X-ray radiation is, how it can be obtained. They also found out how X-ray radiation acts on the substance, on the tissues of the body, and how it is possible to use X-ray radiation. In other words, we still use limited X-ray radiation because X-ray radiation has an ionizing effect, a biologically active effect. That's it. We finished the lecture. Thank you for your attention and goodbye.